Okay, good morning everybody, this is Mr. Steele. I'm coming to you not so live from a DVD player, and I'm doing this because I don't want us to fall behind, and even though this lesson is fairly straightforward, I didn't want to just kind of like throw it out there and give you my notes and call it a day. I want to be able to kind of talk through some of this stuff, give you all the notation stuff that you'll need to work on the homework, and then just let you work the rest of the period on the homework. So in this video, since this is the first one you guys have seen, I'll try to go through everything that was going to be covered in the notes. I will also go through a bunch of examples, and then I'll do a couple try-its or throw a couple try-it problems up there for you, and then after you pause the video and kind of wait for it, I'll let you like check the answers. I'll go through the process for all of them. So okay, this is going to be notes. Let's see. So Monday is notes 40, Tuesday will be notes 41, Wednesday will be notes would you believe that? Notes 42. What we're going to do is we're going to work with functions, and in particular we're going to do operations with them. So we'll call today's notes function operations. And you know what? Since I'm sitting here, let's just do this. Since this is on the whiteboard, I mean whatever. Let's do this in the Cornell Notes format. And so that means that I need to make room for an essential question. I hadn't thought about this up until now, but that's okay. Not a problem. And okay, here we go. So let's start the notes. So first off, our essential question. Well, I mean, the focus of today is going to be both on getting comfortable with the notation and what it means, really. Even though it's on the standard quiz, we've done it before. Like, I want to go through that again, make sure it's really formalized, then actually doing stuff with them. So, let's see. What can we do with functions? And then, well, it's kind of short. Let's say beyond substituting. So that's going to be our focus question of the day. Can't spell substituting. Beyond substituting. So that's what we want to answer, because again, like, we have some idea about functions, as you'll see in a second, but we really don't have a complete picture yet, and that's what today and tomorrow we're going to be focused on as we finish this week out. So okay, let's kind of start. Let's begin and make this part one, and let's talk about actual function notation. Like, that's kind of our starting point. So we want to talk about the notation we use to talk about functions. So like in the beginning of the year, we talked about what it formally means to be a function. Like, we drew graphs and stuff, talked about the vertical line test. That's really not going to be our focus right now. Like, that'll come back a little bit as we go forward. For now, all we're talking about is like the notation itself. So what I'm going to do is let me write down a function using the notation we're going to work with a lot, and then we'll actually go through and talk about all the pieces. So there we go. Our function is f of x equals x squared plus 7. So this is a function. So let me write that. Is a function. And of course the way you read this is f of x, or the function f of x, is equal to x squared plus 7. So the pieces here, like, again, just because I sometimes use these words and I'm not very careful about it, the first part is that x squared plus 7, that thing actually has a specific name. It's not just function or the function equation or something. Like, it's actually called the function rule. So we call that the function rule, or more, generally we call it the rule. And it's also sometimes called the output, because basically we can spit out values for the function, output values, by plugging into that rule. Like, the rule tells us a prescription for how to find values of f of x. F then, like just that letter F, is actually the function's name. So again, when we talk about the function, if we're just calling it the function, that wouldn't be very descriptive. So in fact, we give it a letter name like that. Like, we could talk about f of x like we're doing here. We could talk about g of x. We could talk about h of x. We could call it, whatever we want to do. We could really call it, iguana of x if we really wanted to. That's okay. And then finally, the last piece is x itself. Whatever's inside here, this guy is called the input. Like, that's the value we're going to put into the rule in order to find values. So there are all our pieces here. The function itself, which combines all of it, like it sets the rule equal to the actual notation itself. the name itself right there, and then of course the input we put in. So for example, if I wrote up here something like, I don't know, g of 7 equals, I don't know, 3x cubed minus 11. If I did that, the 7 would be my input. That would be what I would end up substituting in. This guy, that g, would be the name. Like I'm talking about the function g, not other functions. Then of course my rule would be this guy. So again, it's not like this is something we're going to test you on. We're not going to like write out a function thing like this and then say, what is the rule? No, we're not going to do that. This is just kind of the words that I'll be using as I talk about functions all through the lesson today. So that's just kind of our starting point. So the notation itself. Now, of course, like now that we've kind of seen the notation, the question might come up, like, what do we even do with this stuff? Like, what's the purpose of functions in general? Like, what is it that we're going to do? And so what we'll do is let's actually talk about the tasks that are involving functions. And this will relate to standard quiz question number 1. So in fact, most of you are doing pretty well on that, but at the same time, just to kind of give you some context, that's where we're working from. So what we usually are asked to do with functions, at least right now or up to this point, is we're asked to evaluate them for different input values. So for example, we might be asked to evaluate f of, I don't know, say -5. And actually, as weird as it is, I'm going to change the pen color briefly so that we can see this really nicely. So f of -5. You'll see why in a second, not just to be purdy. So f of -5. Just kidding. We're going to evaluate f of -5 for the function f of x equal to, let's see. Oh, we'll just keep it as x squared minus 7. So let's not even mess around. Or x squared plus 7. Sorry, same one as up here. That's a really bad circle, but whatever. My board. Okay, so what do we really do? Well, the way I want you to kind of think about this is what you're really being asked to do is you're asked to substitute. Like this really does amount to substituting, as we talked about when we first ran into this notation. This is just a substitution kind of question. And of course, there are lots of ways to do this, and you probably already know that we're just going to basically plug in -5 wherever we saw an x. But because it's amusing and because I like clip art, the way I always talked about this before is I used to call it Madden math. Because basically what we're going to do is we create a hole to put the input in, and then we're going to go BAM! Right into the hole. So let me say that again. BAM! Right in the hole. So there is Mr. Madden himself. He's kind of the inspiration here. John Madden, the guy who originally sponsored the video game or endorsed the video game, was a college football or a professional football coach for the Raiders for a long time, very successful in the Hall of Fame, and an announcer for a very long time as well, on Monday Night Football and on Sunday games with Pat Summerall, who was a kicker. So what we're going to do, so as I said, I know you know how to do this, it's just kind of fun to talk about the Madden math thing. So what we do is if we want to find f of -5, as we see here, what we're going to do is we're basically going to create a hole to put in that -5 and then substitute it in. So what we get is that f of -5 is going to be our original function with, instead of x, it'll be something squared plus 7 that we're going to put in that input. So we're going to, it doesn't want to do that. Let's see, I want this to be good. Since I've got this multimedia working, let me work with it. So pretend you don't see this, you see nothing. There is nothing here. There is nothing to see here. Okay, so what we're going to do, we just got our function. It's x squared plus 7, but we're going to substitute in -5. So we're going to take that value, -5, and then, let's see, go right over here. And then we're going to go, BAM! Right in the hole. Okay, so it didn't work out so well because I can't really approximate how big that hole was, but whatever, you get the idea. We are going to substitute it in. And of course, what does that give us? It tells us that the value is going to be -5 squared, which is 25, plus 7, which is equal to 32. So of course, the way we write our final answer is either just by writing 32, because that's the value of f of x when we substitute in -5, or we can actually just write that f of -5 equals 32. Remember that that -5 part and the f part, it really doesn't affect our final answer. We're just trying to get a value out or an expression out of our answer. And so there we go. So let's do a second one. Again, I know I don't have to do much with this. It's just kind of entertaining. So you know what, since we've done this before, let's just jump to a slightly harder one. Not that any of this is super difficult, just that we'll try to hit one of the harder versions. So let's now evaluate for our same function. So we'll still use f. Let's evaluate f of, let's go, how about x plus 3? So we'll put a binomial in there for our value of f. So we'll use the same one as before. I'm not going to rewrite it again. Okay, so f of x plus 3. So again, we're going to use substitution. So f of x plus 3 is going to be equal to wherever the input is squared plus 7. And of course, our input value is x plus 3. Like, it's not actually a number, so we're not going to spit out a number as our answer. It's just going to be some sort of polynomial that we'll combine like terms for and then just leave as is, not doing anything else to it. Okay, so what we've got to do is we've got to actually figure out what this is. In order to do that, we're going to have to multiply this out. And when I say multiply it out, I mean really that we're going to FOIL it out. So we're going to see that this is really x plus 3 times x plus 3. And then when we do the FOILing, blah, 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 get the broken sprinklers, we're going to get that first part is x squared plus 6x plus 9. Which again, if you're not sure, just multiply it out yourself. You've done this before. All plus 7, so our final answer is x squared plus 6x plus combining the only like terms here, which are right there, plus 16, which actually doesn't factor, just so you know. And so there we go. We've now kind of used the function notation as much as we really need to. Like, that's what f of x really means. So from here, what can we do? Well, we're going to move on. Let's actually do more with functions. So let's expand what the notation can mean, talking about all the different operations we can do with them, and then just leave you with a couple examples and a couple that you can try. Okay, so what we're going to do now is, now that we've kind of worked with the substituting, it's kind of like we want to go add to our essential question, say, okay, what can we do with functions beyond just substituting? Because that's all we really did, was talk about what the notation meant and how to use that rule and input and get an output, all that stuff. So, right here, basically what we're going to do is we're going to work through and start combining functions. Like, that's really what we mean when we say operations, is how can we combine more than one function together? How can we do stuff with functions? So this is where we actually begin the operations portion of the lesson. So what kind of stuff can we do with functions? Well, the first thing we need is we need some functions to work with. So I'm just going to do two pretty simple little functions here. I'm going to give them to us to work with as we go through. So no, I don't really even need the example. Let's just say, let's just establish what the functions and the rules are. So let's talk again about f of x first. Let's have f of x be, trying to check through my notes, make sure I hit everything here, x squared minus 1. And then let's let g of x be another function that we're going to work with. And let's let g of x be just, I don't know, x plus 4. That sounds good. So two little tiny little functions. Like, that's kind of our establishment. This is just like in a given problem they might say, okay, let f of x be bleu, let g of x be bleu, and then go through and start combining them in different ways. Okay, so what we want to do is we want to hit all the different kinds of operations there are. And in particular, there are 5 that we're going to work with, maybe 6. The first 4 are just arithmetical operations, and that's what we're going to focus on here. We're going to do addition, subtraction, multiplication, and division of functions. So to start out with, let's just start out with function addition. So first of all, what that's going to look like is function addition they're going to give you, or they'll tell you to do, basically by asking you to find something like this. Either f of x plus g of x, which is really clear. It basically says add f of x to g of x, and then obviously combine like terms and simplify. Or they could also write it a little bit differently. I've seen both notations before. F plus g of x. And of course, addition isn't necessarily that difficult. It just basically comes down to combining like terms and, putting everything even, all that stuff. But for the most part, this is really clear. I mean, if you see f of x plus g of x, that's literally what we are going to do. We're going to take f of x, then we're going to add it to g of x. Same thing here. Like, you can see, we're going to add f and g together. So what does that look like? Well, here, basically, we take our two functions, and we'll just write them down here. Like, we're basically substituting the rules in for the actual names. So x squared minus 1 plus x plus 4. So there are our two rules. Right here is f of x, and right here is g of x. Like, they're just sitting right there. Like, all we had to do is put them together. Now we have to add them. Well, looking at this guy, you can kind of see there's not really that much to work with. for x squareds, we've only got this one. So in fact, the sum there is just going to give us an x squared term from right here. For x's, well, we've just got that one, the little x. So it's like we got this guy, we got this guy. We're left with just these guys. So negative 1 plus 4 is going to be plus 3. So our answer here, f plus g of x, is equal to x squared plus x plus 3. So it shouldn't really take that much to believe that that actually makes sense. So the biggest thing to pay attention to is probably just the notation. That when they say f of x plus g of x, or f plus g in parentheses of x, they're saying just add the two functions together. Like, there's nothing really fancy here. Okay, second one. Let's do, I'll draw a line here. I will do this one right below it because it's pretty easy also. The second operation we can do is, of course, if we can do addition, we can also do subtraction. So that's our next step, is how are we going to subtract functions? Well, first, I don't know, let's do a different color. Yeah. This is a quick enough lesson that I might as well do that a little bit. So let's go through and erase the word and write it again. Maybe I'll write it really neatly or something. Subtraction. So we are going to find the difference between two functions. I'll redo that in red. And that's a really bad line. Hard to be a perfectionist to write on one of these tablet thingies. Okay, so subtraction. So first the notation. Well, you can probably imagine that if addition is just f of x plus g of x, you can probably foresee that this is going to look pretty nice and simple also. It's going to be f of x minus g of x. Or obviously we could subtract g of x minus f of x, and that's cool too. We're just not doing that here. So f of x minus g of x, or, same way as before, could also have using this notation, where f minus g of x, or basically x is our input of the difference between those two functions. So to do this, it's basically the same thing, but this one is a little bit more difficult, because when you have that minus sign there, we have to make sure we distribute in that minus sign into both pieces, because we're really subtracting the entire function. So when I go through and do this, I'm going to actually make sure to include everything that I can. So it'll be f of x, which is still x squared minus 1, minus g of x. And I'm going to put g of x in parentheses just so that I make sure that I subtract all of that second function, which in this case is x plus 4. I don't need another parenthesis. Okay, so there we go. Again, don't necessarily need the parentheses, well, but here we really do. We need to make sure we're subtracting the whole thing. So what does this look like? Well, from here, the first part's obviously the same. X squared minus 1, there's nothing being done to it. But then we're subtracting off x plus 4. Well, that means we're going to need to subtract x. So minus 1 times x is minus x, and minus 1 times 4 is minus 4. So our new function rule for f minus g of x is going to be still pretty simple to work with. X squared minus x, so it's like we got that one, then minus 1 minus 4 minus 5. There is our final answer. Again, not really involved in any way. But again, this is definitely a little bit more difficult. We definitely need to be careful here and distribute it in. Because realize if we hadn't put the parentheses there, we would have just subtracted x and still had a plus 4, and that would have given us the wrong actual final expression. So there we go. Addition, check, and subtraction, check. We're good there. So now we're going to move on to the ones that are slightly harder. Okay, so again, addition and subtraction completely done. Now we need to move on to something a little bit more involved, or well, basically just the third of the 4 arithmetical operations you learn in elementary school. And of course that operation is going to be multiplication. So that's where we're going next. So now multiplication, although it is a step up in difficulty from addition and subtraction, really isn't going to be that difficult to kind of grasp. It's just going to come down to, again, recognizing notation and then actually going through and realizing that sometimes multiplication doesn't just get done. It's not just like 4 times 3 is 12. Like, you can't just go that quickly. You have to do a little bit of work. Sometimes it's foiling, sometimes it's multiplying out bigger things than that. It just depends on the problem itself. So again, just like before, first we get the notation. So now this one is going to look a little bit differently, because like in elementary school, when you used to do stuff like 4 times 3, you'd basically do this, right? You'd have 4 times 3, and you'd go 12, and you'd feel really good about yourself. In fact, though, like, we can't use that x notation anymore because x has more important things to be doing. Like, it's actually the input value, and it's expressed in the rules. Like, x can't fill the role of multiplication anymore. So, of course, as you've probably seen, is we imply it a lot and we use a dot. So one possible way you might see this written out is as f of x times g of x, or even f of x g of x. Like, these are both implied to mean multiplication. Like, the little dot in here has to be closed. Just FYI, it does have to be closed. When we get to composition tomorrow, you'll see why. But then if there's nothing there, it's just f of x sitting next to g of x, it's implied that we really mean we're going to multiply those two things. And then finally, just like these guys had kind of the parenthesis notations, so does multiple. Just look away. Okay, yeah, just like addition and subtraction had their own like little parenthesis notation, so does multiplication itself. Like, sometimes we'll see it written this way: fg of x. Like, that, of course, means exactly the same thing. It means we're multiplying f times g of x. Like, those two functions are being multiplied. So here, again, we're using our same two functions. X squared plus 1, or minus 1 is fx, and g of x is x plus 4. And so now we're going to multiply them. So to do this, I am going to use actual parentheses every single time. Like, before, I was getting a little lazy about it. I mean, technically I should have had them here, and then should have like dissolved the parentheses. Like, I already had them right here. But again, in fact, over here I'm going to use parentheses both times. So I'm going to have a parenthesis for f of x, which is going to go right there, and a parenthesis for g of x right here, because I want to remember that we are multiplying them at the end of the day. Okay, so f of x, we know that. It's just x squared minus 1. And g of x, well, we know that too. X plus 4. So from here, like, this is kind of like, okay, did it, multiplied. Except, in fact, we don't want to just leave it. That would be like sitting in your third grade classroom and going, okay, 4 times 3 equals 4 times 3. Yeah, but that's just kind of silly. Like, do something. Like, make it look differently. Change it. Finish it. I want to simplify things. So from here, all we have to do is multiply it out. And of course, when you're multiplying out things like this, we've got 2 things times 2 things. It's just multiplying binomials. So in fact, we're just going to use FOIL. And a lot of the time we will use FOIL. Sometimes we won't. Sometimes it'll be FOIL. Sometimes it'll just be distributing. It just depends on what your 2 functions are. Sometimes it might even be longer multiplication. It just depends. So for this one, I'll actually go through and do the FOILing step. So first, x squared times x is going to be x to the third. X squared times 4, or positive 4, is going to be plus 4 x squared. Minus 1 times x is going to be minus 1x, or minus x. And minus 1 times 4, positive 4, is going to be minus 4. And so in this case, like, there's nothing to actually combine like terms in. Like, it's already there. We got third, second, first, constant. So there's nothing weird there. And in fact, we found our answer. The product of the functions f and g, or f of x times g of x, or f times g of x, is x cubed plus 4x squared minus x minus 4. And again, multiplication does not really pose any sort of issue. So we just have to be a little more careful again. Like, notice as we go from addition to subtraction to multiplication, we just have to get a little more careful. Now, with that said, sometimes multiplication is kind of implied, or it's actually somewhat easier than what we see here. I did say you could FOIL or distribute. So just as an FYI, another way that we could use multiplication would be, instead of actually multiplying 2 functions together, it would be multiplying like a very simple function by another one. So for example, you might be asked to find, say, 3 g of x. And so what that means is basically we're multiplying by a scalar. We're multiplying by this coefficient 3, or this number 3. 3 times g of x. Well, in fact, here it's just the same thing as before, except we don't need as much stuff in here. Like, we've just got 3 times our function g of x, and of course g of x, as it says up here, is x plus 4. So if we have to multiply 3 times g of x, we can just distribute it in. And of course, we'll see really quickly that multiplying by a scalar is really easy. We just distribute, and we cool. 3x plus 12. All there. So there we go. Multiplication, 2 different contexts. This one was actual like function multiplication, like pure functions. This one was, again, multiplying by a scalar, which isn't really that different because 3 is a function itself too. but in fact, neither one really poses that much of a challenge to us. So there we go. 3 down, 1 to go. Okay, so we've got 3 down again, as I probably just said. It's kind of hard because I cut these videos and everything and have to start again. I don't remember what I said because I'm not reading a script. I'm just kind of making it up as I go alongside my notes. But anyway, we do have one operation left, and of course, we did addition, we did subtraction, we did division. We are left, just kidding, X that. I'll pretend I didn't say anything because I don't want to have to delete this. Okay, so we've already done addition, we've done subtraction, then we did multiplication. The only thing we're left with is needing to do division. So being able to divide or find the quotient of two different functions. So just like the last time, let's start with the notation itself. Like, what is it going to look like? Well, there are a couple different ways we could see this. One of them is that it could just say f of x divided by g of x. Like, you can't really be much clearer than that. F of x divided by g of x, it's all cool. So we're just going to divide the two of them. We could also see it in kind of the fractional form, like f of x over g of x. This means exactly the same thing. They're identical to each other. Finally, we could see it two other ways. The first one here, using the little parentheses this way, we don't see this very often. In fact, as I'm writing it, I'm not sure if I have ever seen it before, but in fact it should make sense. I mean, you could have it the same way as you have the other ones. So we could do f divided by g of x, but more commonly I see it written this way, like basically f divided by g or over g of x. So any one of these four mean the same thing. We're going to divide two functions. And this one will be the most involved of any of ours, but at the same time, like as you'll see, it's not necessarily that bad. There's just a couple extra pieces we have to do. So first, f of x divided by g of x. Let's actually go through and do this. So let's divide them. So we want to divide, again using parentheses, x squared minus 1 by, as a divisor, x plus 4. So we're going to divide those two. So now, one thing you could do is you could probably just go, okay, yay me, and write it like that. And, well, that's totally awesome. It seems kind of boring to me, like we didn't really do anything. So, in fact, what we want to do is we want to instead actually do some division here. Like, we want to actually write it out, like, because we can do more than just this in a situation like this where the degree is higher than this guy. So what we could do is we could actually do polynomial long division if we wanted to. So, if we wanted to do that, well, let me think about this for a second. Like, I'm trying to see if in my notes we've ever done that before or asked you to do that. I don't think we do it that much, but in fact, we can do it if we want to. So, let me think. A lot of pressure on me here. Okay, well, what I'll say is that for the most part, what we're going to give you, if we ask you to divide, it'll be in a fairly limited basis. You won't necessarily have to go through and do polynomial division, but at the same time, I'm going to go ahead and do that because I know that we know how to do it. So if we want to divide these two by, x squared minus 1 by x plus 4 to get a final answer, we do need to go up here and set it up. So I'll set it up the old school way, third grade way. We're going to divide x squared minus 1 by x plus 4. But the one thing I will ask you to notice is that there's a missing term here. Like, we're missing the x term. So in fact, we're going to add into the problem a 0x. So x squared plus 0x minus 1. This is exactly the same thing. The problem hasn't changed at all, but now I've got everything accounted for so everything stays lined up and I won't make a mistake. So now I do the old division technique. Synthetic would work also, I'm just not doing it right now. So x goes into x squared, x times x is x squared. X times 4 is positive 4x. Draw the line, change the sign. This will go to 0. This will go to negative 4x. Bring down the negative 1. X goes into negative 4x. Negative 4 times. Negative 4 times x is negative 4x. Negative 4 times positive 4 is negative 16. Draw the line, change the signs. Again, we get a 0, then we'll get 15 down here, and since x can't go into 15, that is our remainder. So it's x minus 4 plus 15 over our divisor, x plus 4. So in fact, this thing is equal to x minus 4 plus 15 over x plus 4. So now obviously not every problem is going to be as involved as this one, but in this case we were able to do division, so hopefully in the triads I hit one that's a little bit easier. But the fact remains, like this isn't actually a complete answer here. Like we can't just like leave it like this. Just like we couldn't stop here because this wasn't simplified enough, we can't stop here because we're actually missing one little piece. And that is that this denominator here, x plus 4, actually could cause problems for us. So think about it this way. Like what we're doing when we do this is we're finding a prescription for the quotient of these two functions. We're saying that if you plug in 4 into the quotient of these two, like if we want to find f of 4 divided by g of 4, we would basically use this new expression. Like we could substitute 4 in there and get it in. But the problem is there are values that could make this expression non-existent. Like there's a place where this function doesn't exist. And in particular, that place comes from the quotient. So in fact, in order for our answer to be 100% complete, we need to account for the possibility that this thing could be 0 and say, okay, we can use any x value except for that one problem, or however many problems there happen to be. So in this case, we look at this guy and say, okay, how could this be bad? And of course, the answer is always the denominator. Like the denominator, if it equals 0, that would mean we would be dividing stuff by 0. And as any calculator can tell you, anything divided by 0 doesn't work. There's in fact only one person in the universe that can divide by 0. That is, of course, Mr. Chuck Norris. So now Chuck Norris can divide by 0. You are not Chuck Norris. So let's make sure you remember this. Not you. So in fact, you cannot divide by 0. So what we have to say is that this function rule, this works, either one of these, but really this one since this is the best one. This function rule is perfect for f divided by g of x, or fx divided by g of x, except when x equals negative 4, or except when x plus 4 equals 0, which is the same thing as when x equals negative 4. Like hopefully you can see why that comes out. It's the same way as finding a pivot before. So if x equals negative 4, that doesn't work. So we add on to our answer one little thing. Like I draw a little comma or a semicolon, your call, and we say that x cannot be, so x does not equal negative 4. Because if x doesn't equal negative 4, well, this formula works out great. If it does, well, we'd better be Chuck Norris because only Chuck can divide by 0. So our final answer is this. It's the actual quotient itself, so the two pieces are the quotient that we get from dividing or whatever expression we have for that quotient, and then the restrictions. And the restrictions are the numbers that make our denominator go to 0. So make the denominator equals 0, because again, only Chuck Norris can divide by 0. And now, before we go on and do some more of this, I'll actually do another one here maybe or something, and then we'll do some triads. Just wanted to say, just because it was amusing, when I went to look for a nice suitable picture of Chuck Norris and found the one from Dodgeball, which is probably his best cameo ever, I found this really cool website. So let's take a look at it really quickly, just because it entertains me. And so this place has like tons and tons of Chuck Norris facts and cool little images. So the first one here is a Chuck Norris, I think, Yu-Gi-Oh card. It appears to be written in another language, so in the event that it says something inappropriate, I'll just move down really quickly. Not awkward at all. There's the one that I stole. Again, epic scene, pivotal scene in the movie Dodgeball, a true underdog story, starring Ben Stiller and Vince Vaughn. And that guy that was in Avatar. From there, we've got the Chuck Norris Whopper. Well, we can't see it all, but again, I'm going to use context clues to assume that that does say Whopper. We've got the Chuck Norris Attorney. It must be someone else named Chuck Norris. Not really that funny. That one doesn't really amuse me. This is Chuck Norris's toilet paper. That is, in fact, a roll of cheese graters. Laugh if you want, kind of gross. Here's a classic one. This is one of the first Chuck Norris facts, if I remember right. Guns carry Chuck Norris for protection. Whatever. And then, of course, we've got Chuck Norris is the 11th commandment, using, I think, a Chuck Norris Karate Commando view. And, of course, the absolute best one on here. Error, divide by 0. See, it's like they even knew what we were talking about. Your three options are either quit, go to where the place was where the error came from, or Chuck Norris. Like, this is probably, I probably should save this. In fact, I'll just keep it up here. I'll copy it so I have it for my own amusement. Maybe I can turn it into a poster or something. So anyway, Chuck Norris facts, totally fun. Getting back to what we were doing though, remember what we were doing is we were doing division, so we had a bunch of notations that all meant the same thing. Some were kind of fraction-y, some were the little division symbol e. Basically it amounted to dividing one function by another, which we could do with long division, or even just kind of write it that way if that was, if the thing wasn't going to work that well. And then of course in our answer, the things we needed were the actual quotient we got by dividing, and then a restriction that accounts for the possibility that the denominator equals 0. So that won't happen every time, but that is an important piece of our actual function rule, because that's something that's changed now. Even though I haven't talked about domain before, the domain of the function has been changed from what f and g of x were into something that's slightly restricted more. So again, we'll do another tryout with this one in just a second. Alrighty, so I think at this point you've gotten enough of the gist of everything, and you've got enough Chuck Norris jokes that you can kind of start practicing a little bit. So before we actually get to the homework, what I'd like to do is I'd like to give you a couple to try that I can then go through, and so we can make sure you've totally got it. So what we're going to do is we're going to do a massive try it. It's going to be set up very similar to the last one, except this time I'm going to give 3 different functions, all 3 totally different looking. So here's what we're going to be given. So 3 different function rules. Given that f of x equals x plus 2, we'll go g of x equals x squared plus 7x plus 10, and h of x equals 2. Find all of the following. So let's see, I have a bunch written here. Some of them are going to be really quick, some will take a little bit longer, it just depends. So we'll go A, so give me a second to write these out. B, I'll try to use this simpler, quicker notation just for simplicity. C, so again, we're mixing in a bunch of different functions, but the same rules will apply. D. So switch the notation on you, didn't really mean to, but that's cool. Again, there's no real difficulty in figuring out which one's which. Let's go one more. I don't know why did I do that. F of x divided by h of x. Okay, so there we go. These are the ones I would like you to try, A through F. And so what I ask you to do is, whoever's got the remote, if you can please pause the video for a couple minutes. I mean, I don't know, maybe 3 to 5 minutes, 4 or 5 minutes. That way everyone has a chance to kind of go through these, talk about it with each other, and then come back to the video and I'll actually explain everything. So go ahead and do that right about now. Alrighty, hopefully you're back now. So what we're going to do is we're going to go through all these examples so you can or try it so you can kind of check yourself and make sure you got it. So this kind of covers everything we did today. So first one, for A, g of 4, that just means we're basically going to substitute in g of 4, remembering that we're using Madden Math. So like bam, putting that 4 right into the hole. Because of course our input is going to be 4. So what does that look like? Well, g of x is x squared plus 7x plus 10. So g of 4 is going to be just substituting in 4 there. So what was x squared plus 7 times x plus 10, we now have 4. So this guy becomes 16 plus 28 plus 10. These guys are 44. This one is 10 equals 54. So in fact, there we go. Our first one, A, the answer is 54. So just a number, because we're substituting in a number. Okay, second one, B, f plus g of x. So we're just going to add the two of them. That'll mean it'll look like x plus 2 plus x squared plus 7x plus 10. So now I should probably be a little more careful and put them in parentheses so I see everything. But either way, combining like terms now, if we dissolve the parentheses, for squareds, we've just got x squared. For x's, we've got 1x plus 7x equals plus 8x. And then plus 2 plus 10 is plus 12. And of course, you might see that and go, oh, I can factor that one. Yeah, you can factor that. It'd be a diamond. You'd get x plus 6 times x plus 2. But why do extra work? Like, why make it more likely that you'll make a mistake? In fact, I just call it a day right there. It's cool. So there's our B. So C, h of x, or h minus g of x. So h is 2. Again, we do need the parentheses here to be careful. G of x is x squared plus 7x plus 10. So now, of course, we're subtracting two functions, so we do need to distribute it in. Notice that that first function, h of x, is just a scalar. It's just 2, but that doesn't really affect anything here. It's just just another function. It's just really simple. So from here, we're going to get 2 minus x squared minus 7x minus 10. So notice each one minus times x squared minus times positive 7x minus times positive 10. Then from here, for our final answer, starting going from highest degree to lowest, we'll get negative x squared minus 7x. I mean, those are the only x squareds and x's in the problem. Then we have 2 minus 10, which is negative 8. And once again, there we go. So nothing really difficult so far. Again, pretty simple operations. Okay, let's move on to D. So D is the first place where it starts to get a little bit harder. So we're going to divide g of x by f of x. And so let's just go ahead and let's just write it out. G of x, which is x squared plus 7x plus 10. We're going to divide it by x plus 2. So let's just do the division step real quickly. This will be x squared plus 2x. Draw the line, change the signs. 0, we'll get 5x. Bring down the 10. X goes into 5x plus 5 times. So we'll get 5 times x is 5x. That's good. 5 times 2 is positive 10. Draw the line, change the signs. You get 0, 0. Oh, we get remainder 0. That's cool. That's because x plus 2 is a factor of x squared plus 7x plus 10. So in fact, our answer here to D is going to be x plus 5. But again, remember, our answer needs a quotient and it needs a restriction. So when we look at our original expression here, g of x divided by f of x, what is the value that would make this denominator equal to 0 and prevent anyone but Chuck Norris from doing it? Well, clearly, if you think about it, it's fun doing algebra sometimes, making zeros and ones. The answer is that x have to be equal to negative 2. So our restriction is that x cannot equal negative 2, because then the value wouldn't make sense. We wouldn't actually have an answer. So there we go. So quotient, restriction. That's probably worth pointing to. Quotient, restriction. Again, we'll use restrictions a lot more in future parts of the class. Okay, so that's D. Moving on to E. So f of x times h of x. So I'll use parentheses. F of x times h of x. Well, that's kind of nice. Times a scalar. I can rewrite it this way. Probably see it this way. 2x. That's a really bad equal sign, by the way. Sorry. 2x plus 4. So there's our answer for E. Okay, finally, last one. That's a bad circle, by the way, too. Last one, F. So we want to do f of x divided by h of x. And so there we go. There is our quotient. If we divide it, well, actually this one's not going to do much. I mean, we could rewrite it this way. We could divide it into both of them. It would be like 1/2 x plus 1. I mean, that's cool too. I mean, both of these are fine. I would accept both of them. And again, like, the reason is that there's not really that much that we can do. But again, there's our answer. We divided it in. It's basically the same thing as multiplying by 1/2, as you can see. From there, though, otherwise, like, our question would be, okay, we have our quotient. What are our restrictions? So our restrictions are anything that would make the denominator equal to 0. So the question is, when is 2 equal to 0? And the answer is never. Like, 2 is never equal to 0. It's just a different number. They're just not the same thing. So in fact, we don't have any restrictions. And in order to finish this problem off, we can just box it and say, there we go. That's my answer. So that's just my quotient. Again, in this case, it actually would have been okay if you'd gone with this one. But I think it's best to actually do some division, like to divide each piece into it. So there we go. We've now done an example of each one, evaluating just a function value, adding, subtracting, dividing, actually twice, and then multiplying. So we've kind of hit everything here. Okay, so with all that said, we've basically done everything we need to do. Like, we've hit everything, we've practiced a little bit. Kind of review what we've done today. First, we talked about the idea of function operations and, of course, what a function meant. Talking about some of the anatomy, some of the pieces and names for things that are in functions. We talked about the idea of Madden math, meaning that we're plugging something in right into the hole that's created by the input. And so again, like basically we were evaluating or substituting. From there we started doing different operations that we can on functions, starting with addition and subtraction, which were both pretty easy, aside from the fact that we do need to be careful to use parentheses as much as we can. Same thing with multiplication. Sometimes it's easy, as we saw in our triads. Sometimes we do have to FOIL stuff out or multiply it out a little bit more. And then from there we did division, which was the most involved one, not just because it's kind of awkward and we have to do things like polynomial division, or canceling and stuff, but also because like there's this idea of restrictions, because when you divide by something there's a possibility that you could be dividing by 0 at a certain input value, and so we have to say nope, that's not okay, because again, you're not Chuck Norris. Only Chuck can divide by 0. And then finally we just practiced a little bit. So at this point we're pretty much done, so it's tempting to just call the entire lesson over. But in fact what I'd like to do is I'd like to go through just really quickly and finish out these Cornell notes. Like normally it would be better for you to actually go through this on your own at another time, but since I'm not here and this video is under 45 minutes at this point, I just want to go through and like use this time wisely and go through it. So I'm going to go back through all these notes that you already have written down as best you could. Let's just add some pieces. So looking at it, we have to think about what's missing. So the first thing that we're missing is the header. So the date on Wednesday will be November 9th. That's the day you're watching this, I should hope. So of course there's my date. I should have had that all the way through, but that's okay. I just forgot. And now what we want to do is let's add some questions. So we already had an essential question here. What can we do with functions beyond just substituting? And so the first thing we talked about was notation and evaluating. So coming up with a higher level question for this is kind of hard, but I guess we can throw one in here. So let's go this way. What are the parts of a function? So again, it's not necessarily a super valuable question, but it's not bad either, because it's not just level 1, it's not just saying what is a function. You're talking about all the distinct little parts of a function. And in fact, well, that looks pretty good to me. Again, like that's okay. It's not a great question, but it's better than nothing. So, and again, we saw all that stuff. We saw we could evaluate with it. I think we already know that, so it's not worth taking our time to put a question down for that piece. So the second part, let's see, like addition, subtraction, multiplication, none of those were really that difficult, I would say. But at the same time, like they all kind of like, it was important to like use parentheses to make sure that we covered stuff like distributing and foiling. So let's focus our question on that piece. So how can I use, let's go with parentheses, and I may completely butcher the spelling here. Parentheses, probably with an E, whatever. How can I use parentheses to do function operations correctly? Because again, I think that's the most important piece to get out of this little portion of our notes. Because again, it's not like the skills are hard. It wasn't even necessarily hard to recognize, but it was important to use that to help us organize, particularly here in subtraction and up here in multiplication, because both of those needed us to actually have those parentheses to get it completely right. So again, our question for the question column, how can I use parentheses to do function operations correctly? And so again, if you have other questions to throw on there, you can. For example, what is she doing here? But that's okay. It's not a high-level question. Samara is always in our classroom. Okay, moving down next. So the last thing we covered was division. That was kind of the hardest one. And the notation was kind of weird, but I think probably the clearest parts, or the parts that need the most analysis or attention, would be probably this one, because we actually had to use long division. And then also even more interesting or notable would be this part about restrictions and Chuck Norris, only because that's completely new. So I'm not even going to worry about the I'm not going to worry about this part right here with the division part. Let's worry about the restrictions. So, what are restrictions how do you find them? So specifically, how do you get where those restrictions are? And let's see, and that's actually pretty good. That's actually a pretty good question. So, what are restrictions, and how do you find them? So let's go with that as our question. So what are restrictions and how do you find them? So again, to answer our question here, not that we have to right now, the restrictions are the values that could make the denominator or the divisor of our division equal to 0, and we find them by making that denominator or divisor equal to 0. And then it's cool, because again, only Chuck Norris can divide by 0, and you are not Chuck Norris. So putting that in equation form, you do not equal Chuck Norris. Now, of course, if you happen to be Chuck Norris and you're watching this video, huge fan, you rock, dude. Don't kill me. And finally, for this part, this was just practice. So I wouldn't even say that this is necessarily to write a question for, like we just practice. So if you want to, you could just say practice. So okay, so we've done all that. So let's go and write a really short summary here together, or most likely while I'm doing it here, just because I need to model this more for you. So for our summary, like what can we hit? Remember that our major goal of the summary is to answer the essential question, to answer what can we do with functions beyond just substituting. So we need to answer that as well as kind of cover everything that we do. So to kind of start off with, let's kind of hit something from our first section. So the parts of the function, what are the functions? So like let's put it this way, like I've kind of used this notation throughout the day, but okay, let's see if I can find my pen here. Okay, so functions are, well, they're basically rules. Are rules for finding, kind of awkward to say, isn't it? Functions are rules for finding outputs. Let's do that. Yeah, finding outputs from inputs. Hopefully this is readable. This is really awkward to write on my little tablet thing because it's like on the corner. So functions are rules for, that made that F worse. Functions are rules for finding outputs from inputs. You can, well, what do we do with them? Because what can we do with functions beyond just substituting? You can add, subtract, multiply, and divide them. And then what else? So add, subtract, multiply, and divide them. So that kind of answers our essential question, so we're good there. But like, what was it about that? Like, what did we do in there? Okay, so so on this page we kind of asked our question over here, how can we use parentheses to do the operations correctly? And over here we had restrictions. But let's see. But we need to use parentheses and note restrictions we need to note restrictions for division at least. So I'll put that there. I'll put a little dash there so that we kind of separate that out. So functions are rules for finding outputs from inputs. You can add, subtract, multiply, and divide them, but we need to use parentheses and note restrictions for division. I would hope that you would be able to say that this wasn't very hard. But what do you call it? What else? Well, I don't know. Let's go a little tongue-in-cheek. Last thing that we learned today, hopefully, is only Chuck Norris can divide by 0. And so there we go. Well, that's just meant to be kind of funny. The rest of the summary is pretty decent. And again, like Cornell Notes, not necessarily as valuable for an easy kind of lesson like today's, but for the most part, still a very valuable tool to help you learn everything. And again, if say I gave you 5 minutes before the test on Chapter 7 and you had to kind of review everything, this would very quickly kind of hit everything and get all the important stuff into your mind. Get the idea of restrictions. It would kind of mention about parentheses so that you kind of get that in your head. And then it would also kind of mention the Chuck Norris can divide by 0 thing, which, even though it's just meant for humor, also kind of helps you remember the entire purpose and meaning of restrictions. So I would say this summary is perfect, and our lesson is pretty much complete here. So for the rest of the period, work on whatever the homework is that I choose to assign to you. And yeah, I will see you tomorrow, barring an apocalypse or something tonight. So anyway, this is Mr. Steele, signing off. Have a good day.